Okay, we're going to do a couple of more problems practicing induction. It's very, very, very important. You need to be proficient at it, and also I want you to get used to writing it the way I'm asking you to write it. That's going to be a requirement. Okay, so let's do this question together. Prove that if n is a natural number, then one times 3 plus 2 times 4 plus 3 times 5 plus 4 times 6 and so on up to n times n plus 2 will equal n times n plus 1 times 2n plus 7 over 6. Okay? We are going to prove that. Okay. Now watch carefully, follow along carefully, because I want you to write them this way. People learn different ways of doing induction, and that's fine, but in this class I want you to do it this way. Okay, so what we're going to do is we're going to start off by saying let S be the set of n in the natural numbers such that 1 times 3 plus 2 times 4 plus 3 times 5 plus 4 times 6 and so on up to n times n plus 2 equals n times n plus 1 times 2n plus 7 over 6. So S is the set of natural numbers that satisfy our formula. Okay? Now, we want to do two things. Well, let's actually think big picture. We want to show that S equals the set of natural numbers. That's what we want to show. We want to show that every natural number is in S. Okay? And the way we're going to do that is we are going to, let me not use an arrow. That's not a good idea. Okay, we are going to show that 1 is an element of S, and then show that if n is an element of S, then n plus 1 is an element of S. Okay, so there's two steps. Show 1 is in S, step 1. Step 2, show that if n is in S, then n plus 1 is in S. Okay, which is a conditional statement, right? That second step is a conditional statement. How do you prove a conditional statement? Well, there's a few ways, but we're going to do it directly. So we are going to assume the hypothesis, show the conclusion must happen. So there's two steps, but step 2 is broken down into 2 parts. So it's like there's 3 steps. 1, 2, you can't read that. Hang on a second. 1, 2, 3. What's 1 called? It's called the base case. What's 2 called? It's called the inductive hypothesis. Okay, that's what we're going to do. So, step 1, base case. Let's show that 1 is in fact in the set S. Okay, well, let's do some scratch work first. Let's figure it out. Okay, because some people are not quite clear on the difference between scratch work in order to figure out a proof and writing the proof. So let's do some scratch work here. I'll do it in gray. Scratch work is we're going to try to show that 1 is in S. Okay, so what will this left hand side of the equation look like when n equals 1? It'll just look like this, 1 times 3, and then that's it, right? We want to show that that would equal this. How would that look? It would look like this, 1 times 2 times 9, won't it? Over 6. Are those in fact the same? Well, let's see. Let's work towards the middle and see if they match up. So that's 3, right? And this thing over here is 18 over 6. And isn't 18 over 6 equal to 3? So there we go. Now that's our scratch work. Okay? That's not the proof. Proofs are made up of sentences. That's important, okay? Proofs are made up of sentences. So I'm going to write a sentence. I'm going to write, notice that one times 3 equals 3, which is equal to 18 over 6, which is equal to 1 times 2 times 9 over 6. You see, I took what I figured out in my scratch work here, okay, and I'm writing that into a sentence. And now I can erase that scratch work. Okay, and now, so what does that sentence allow me to conclude? It allows me to conclude that 1 is in the set S. Thus, 1 is an element of S. Okay, excellent. So that takes care of step 1, the base case. Okay, now, what is our inductive hypothesis? Our inductive hypothesis is, suppose n is in the set S, or if you prefer, you can use the letter k. That variable does not matter, but I'm going to stick with n, okay? Suppose n is an element of S. Okay, what do I want to do? I want to show that n plus 1 is an element of S. Okay, now here's a really good idea. I said suppose n is in S. I had better write down what that tells me. So if n is in S, what does that tell me? It tells me then 1 times 3. Oh, here, let's just save some time. Let's copy and paste. Oh, whoops, sorry. Okay, there we go. All right, now what is it that I want to show? I want to show that n plus 1 is in S. This is going to take some scratch work. So let's change to gray, and let's do some scratch work, okay? So first question, what would this look like for n plus 1? It would look like this. 1 times 3 plus 2 times 4 plus 3 times 5 plus 4 times 6 and so on up until what? N plus 1 times n plus 3. Do you agree with that? That's what the left-hand side would be. Okay. What would the right-hand side be? The right-hand side would be n plus 1 times n plus 2 times 2n plus 1 plus 7. Agree? Over 6, right? So I want to show that that's true. What I just wrote in gray, I want to show that that's true. Okay? Now, I am almost guaranteed to need to use this. So therefore, it is a remarkably good idea to go ahead and write the term right here that comes right before this. So let's just add that in there. It would be n times n plus 2, right? And what's the reason why? Because then this you see to be exactly that, which means I can replace it with this. So let's do that replacement. N times n plus 1 times 2n plus 7 over 6. And then it's going to have after that the plus n plus 1 times n plus 3. Okay? And I want to show that that equals n plus 1 times n plus 2 times 2. By the way, what would that be? 2 times n plus 1 plus 7. That would be 2n plus 2 plus 7, right? Over 6. All right. Now on the left, I would like to do that addition, which means I need a common denominator. So let's put a 6 here so that I can put a 6 there so that I can add those two fractions together. Okay. And also, I'm going to give some advice to go ahead and multiply those out. Let's see what we have. Put them in polynomial form. So this one's going to be 2n cubed plus 9n squared plus 7n over 6. And we're going to add to that this fraction, which is 6n squared plus 24n plus 18 over 6. Okay. On the other side, we're trying to get n plus 1 times n plus 2 times 2n plus 9 over 6. Okay, now add on the left. You're going to get 2n cubed plus 15n squared plus 31n plus 18. And if you just factor that guy, guess what it factors into? It factors into n plus 1. But here, let me write it like this. Now, I'm just going to copy the right-hand side here. Okay. Now, on the left, factor the numerator, and it factors into n plus 1 times n plus 2 times 2n plus 9 over 6, and that equals the right-hand side. So now we have the left-hand side equals right-hand side, and that's good. That's our scratch work. Okay. Now that is absolutely 100% not what I write in the proof. Because if I do, here, let me show you what I mean. If I were to write, How about we'll use the word hence, and since I used then in the previous sentence, I'll use hence this time. Now, if I were to write all of this stuff, let me just take it and slide it up there. I'm going to spend a few minutes talking about this because some people still haven't caught on to the difference between doing scratch work to figure out how to do a proof. Let me restate that. There's some people who still haven't figured out the difference between the scratch work that you do to figure out how to write a proof and writing the proof. Okay, so if I turned that in right there as it is listed, it'll get marked wrong. And here's the reason why. So, a couple things. Let's count the number of lines that are here as it is written. I'm not asking you how many lines do you think this person meant. I'm asking you how many lines did they write. You see, and this is the problem, is that what they meant and what they wrote aren't the same thing. So I'm not going to ask you what they meant, because when I read a proof, I don't try to figure out what you meant. I look at what you write and I grade what you wrote. Okay, so as it is written, let's count the number of lines. There's one line there, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, somebody who says, no, all that gray stuff is one line, I say, okay, I hear what you're saying, and what I'm saying is that you're wrong. It's not. Okay? That gray stuff is 5 different lines. As it is written. You may have meant to write one long line, but that's not what you wrote. You wrote 5 different lines. Okay? Because if I were to put punctuation on here, I want to read this line as we go across. It says, hence, this stuff equals that. And that is a complete sentence, which means there is a period right there. This is starting a new sentence. Okay? Now, so there's a couple things wrong. Number one, I don't want to say incorrect, but just poorly written, is the fact that why is there no words introducing this sentence here? That is very awkward to me. A sentence that is simply an equation and nothing else. No word at the beginning, nothing. It's not wrong, but it's very awkward and not well written. A mathematician reading that would say, whoever wrote that is not a good writer of proofs. Okay, not necessarily wrong, just not well written. But here's what is wrong. When you write a proof, every line must be true based upon only itself and what you have written previously. Okay? This right here that's what we're trying to show, isn't it? In other words, line 6 says what I'm trying to prove is true, which means that you are claiming that the proof is done at the end of line 6. You are claiming we are done with the proof. And there's 2 glaring problems. One is somebody's going to say, then why did you write 4 more lines if you're done? And when I ask people that, usually their answer is, because I'm not done. And then I say, well, you wrote that you're done, because that line number 6 right there says, I'm done with the proof. Because what I highlighted in yellow is what you're trying to prove. And line 6 says, hence, that's true. Okay? So first of all, why is there 4 other lines after that? And second of all, there's nothing written in lines 1 through 6 that convinced me that that stuff highlighted in yellow is true. And the reason why is because the person writing this has put the justification for line 6 in lines 7, 8, 9, and 10. Is that how we write a proof? Do we write a sentence and say this is true and then spend 4 lines after that showing that it's true? No. Every line has to be true based upon what is written up to that point. Okay, so that's why this is wrong. I hope that the people who are struggling with that are starting to understand what it is they're not getting. Okay, now, next thing then is, how do you write it correctly? Okay, well, first of all, one thing I'm going to do is I'm going to take the scratch work and I'm going to move it back out of the proof again, since it is scratch work and doesn't belong in the proof. It didn't all come. Just a minute here. Okay. So, there's nothing wrong with the scratch work, okay? It's beautifully written. I'm just saying it's scratch work. It's not the proof, okay? All right, so this is where we're starting here. This is our goal. We want to finish with this. How are we going to get there? Here's how we're going to do it. We're going to go from the start. We're going to go to here, and then here, and then here, and then here, which the equal sign then is going to allow me to go to here, which is going to allow me to go to here, which I can skip over the next one because those two are just the same, okay, to there, to there. You see, now, let me erase those 4 equal signs, and there we go. Another way to do it is for me to write like this. I could say we're going in a U shape. Okay. So, when I write the proof, I know it looks small up there, but I want you to be able to see everything. Okay, I'm going to write hence 1 times 3 plus 2 times 4 plus 3 times 5 plus 4 times 6 equals, oh, I'm sorry. I threw myself off because I was saying it wrong. Why did I say equals? There's still more to write. Plus dot 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 plus n times n plus 2 plus n plus 1 times n plus 3 equals n times n plus 1 times 2n plus 7, whoops, plus 7 over 6 plus n plus 1 times n plus 3, which equals, no, that's very important. Did you hear what I just said? I didn't say equals, I said which equals. We'll get to the importance of that word which in a few minutes after I finish writing. Okay, so which equals what? 2n cubed plus 9n squared plus 7n over 6 plus 6n squared plus 24n plus 18 over 6, which equals 2n cubed plus 15n squared plus 31n, whoops, plus 18 over 6, which equals n plus 1 times n plus 2 times 2n plus 9 over 6, which equals, and now what I have written in this right hand column over here is pretty much the same all the way up. So I'm going to go straight to this n plus 1, n plus 2, 2 times n plus 1 plus 7 over 6. You see, when you do your scratch work, sometimes after stepping back and seeing the scratch work, you realize, oh, you know, some of the steps that I just made are so tiny little steps where I didn't do very much in one step that when I write out my proof, I can probably combine a couple of steps. And that's basically what I did. I went from here straight to here in one step, which is totally fine. Okay. Okay, now I'm going to erase the scratch work now. We're done with that. Just bear with me here. Okay, let's look at our proof. And if you have questions about what I've been saying about the proper way of writing proofs, and if you're looking at that and you're saying, I don't see how that's any different, don't worry, I'm going to address that, okay? But let's just finish first really quick, okay? So what is it that I was just able to show? Do you realize what I just showed? I just showed that n plus 1 is in the set S. Whoops. So our base case, we showed that 1 is in S. Our inductive hypothesis, we assumed n is in S. We showed n plus 1 is in S, which means, therefore, by the principle of mathematical induction, S is the entire set of natural numbers. And we are done with the proof. Okay? All right, now, a couple of things to say. Let's get back to, what if somebody's looking at this part here and they say, I don't see how that's any different than what you said is wrong. Okay, here's the difference. This is one line. Here, look, let's count the lines. 1, 2, 3, 4, 5, 6, 7, 8. This whole thing is line number 6 because that is one sentence. That is not multiple sentences. It's one sentence. That's why it's important, the word which. You see, look at, there's a bunch of equal signs, right? But there's not a left and right hand side of each equal sign. What I had written before that I said was wrong, there was an equation with a left and a right side. And then under that was another equation with a left and a right side. That's not what's going on here. This is it is multiple equations, okay, that are put together to make one sentence. So, just one second. So I'm going to read this very long sentence. I'm not going to read all the numbers, okay? I'm just going to substitute the word this everywhere I see an expression. So you see, it's very important to understand the difference between an expression and an equation. Every time I see an expression, I'm going to just say the word this, okay? But listen very carefully to the words I say when I hit an equal sign, okay? Follow along with me. Hence, this equals this. That's one sentence, right? But the sentence isn't done because listen to what I'm going to say. Which equals this, which equals this, which equals this, which equals that. That was all one sentence. You may say it sounds like a run-on sentence, but I'd rather write a run-on sentence that's mathematically correct rather than breaking it up into 5 separate sentences that makes the proof not logically correct. Okay? In fact, you can even do this, which is actually much nicer even, but it all depends. I could take this right here. I didn't have to write it under there. I could have stuck it right there. And now I do have to go down because I simply don't have any more room to move to the right. I'm at the edge of the screen, so so this part here, let me put right there, but I'm going to indent it because it's still the same sentence. Okay, and then this. And then this. And then I don't quite have enough room to squeeze that in. I'm going to have to put it down here. So now do you see how that's all one long sentence? And now I can take this stuff and move it up. Okay? So I hope you're starting to see that, those of you who I have made comments on some of your guys' work of saying this is not how you write a proof, this is scratch work. That's why I'm doing this discussion with you, okay? I hope it's starting to make sense. Oh, and one other thing too, This is how I want you to do the induction proofs in this class. I want you to write this. I want you to write this, and this, and this. You may have learned induction already in a different class with a different professor, and you may have written it differently in that class. But this is this class with me, and I want you to write it this way. And there's a reason why. I'm not saying the other ways are incorrect, but this class is set theory and logic. So I want you to write your proofs using your inductive proofs is what we're talking about here. Let me start that sentence over again. This class is set theory and logic, so I want you to do your induction proofs using the language of set theory. So I want you to write, let S be the set of natural numbers that satisfy this equation. Show that 1 is an element of that set. Suppose that n is an element of that set, and therefore that causes n plus 1 to be an element of that set. This class is set theory and logic. I want you to use the language of set theory in your induction proofs. If you don't, I'm just going to kick it right back to you. Okay? If you like writing your induction proofs another way, then you're welcome to do that in all other instances except what you're handing in to me to be graded in this class. You want it to be graded in this class, you need to write them this way because this is a class on set theory. So I want you to use that language of sets to do these proofs, okay? I said we would do 2 today, but we spent a long time on this one, and so I think I'm going to save the second example I was going to do with you, and I'll just make that be the next lecture. So we'll stop here for today.